Okay, all right, folks, so we are going to get started today. And today we're going to go over some examples in the book, which we are using the Schrödinger of wave functions to the calculation. So we will show you how we actually do the calculation. So this is the generic way to do the calculation. So let me show you what we do. We are going to use the wave function that we did last time, and this will be a very quick calculation. I think this is the item number 4. We're going to use what's called expectation value. Of observables. For particle in a box. And there is no magic, so to speak. How do we calculate this? We use exactly the same method as we did it before. Suppose we have an operator that's called O. We'll put a hat on the top. This is an operator. And we want to calculate expectation value of this operator. And I'm going to write out what actually expression look like. You see I have 5 sub n star, and this is my wave function for the particle in the box. I have an operator, O hat, another n, and this is the one dimension, so I just over dx. And this is how do we do the calculation. Now if we want to calculate any properties, we can do the calculation. For instance, if we want to calculate expectation value of x, then this operator will become xp. If we do that px, we do the same thing, and this will be px hat, like this. So that is the calculation in this way. These are called expectation values. You can directly calculate. And I would like you to look at a page. On my page 35, for those of you have electronic version of the book, probably it's not page 35. Maybe a web page difference. I don't know. What's the page number? That's example 8. This is example 8. What is the page number, example 8, in your electronic version? You've got a physical book already?
I sit at the home. I have pictures of it.
Oh, okay, cool. All right. Is that what's the page number? 30. You got a 30. Whoa. Okay, they are a huge difference. Okay. So that's example 8. Expectation values of position and momentum. So that's what I'm talking about. And I give you 3 minutes, maybe 2 minutes to read it. Let's give you 3 minutes to read it. So that's how we do the calculation. Example 8, 2 minutes. I'll check you guys. finished, let me know. If you have a question, also please let me know. Good. Everybody's good? Good. Any questions? Any questions? Okay. So, and as you notice, something very interesting going on. If you have a x squared like this, the results is almost identical to the classical problem. Remember classical problem last chapter we discussed this. So they are almost exactly the same. Okay. So, and this called expectation values like that. Now I want to give you some additional ideas what about this operator can do. We could also have a transition matrix elements. Matrix elements. So this is actually a very simple change. It's not huge change. It's just a very simple change. And you're going to learn so-called transition matrix elements. And this part makes things rather straightforward in the sense that if you talk about transition matrix elements, you're going to have a transition between these two states. So the matrix elements, this time I cannot use a simpler notation. I have to tell you which state that I have. Suppose I start with one state that's called phi n. I use the letter n representing that. And now you want to transition to another state. So now you can see my two wave functions, it's not the same wave function now. This is called a transition matrix elements. Written the following way, we have n star, and then x, phi, m, and dx. Now in this case, the expression is look like this. We call it transition matrix elements. Essentially, if you have two levels, so this transition from n to m like that. That's called a transition. I think it's a very simple expectation value. Have two wave functions the same, but now if you have transition matrix elements, with these two values will be different. One last part, which we covered last time already, but I just want to show you, summarize it. Time-dependent wave function. This essentially is a review of what we discussed last time. For the pure state in the time dependence, we will write the following way: t equals 0. For the time dependent, we'll e to the negative I e n t over h bar, and have t equals 0 case. If you have a pure state, you will end up going like this. So for the pure state. And then you can also calculate, folks, let's call this phi guys called phi n t like that. Okay, so that will be this case. If you have a mixed state, you do the same thing, except mixed state case. Let me just use 2 as example. If you have mixed state, C1 phi 1, so C2 phi 2. For a mixed state, you still carry this coefficient in the front. And IE1 t over bar, phi 1, C2, e to the negative IE 2t h bar over phi 2. If you have a mixed state and you have a wave function like this, essentially it's no different except you plug in this factor, plug this factor into it. Now, if you calculate expectation value, you do the same thing. And suppose this is your phi psi t like that, and equals. This is the psi t. And when you calculate expectation value, you do the same thing. You will calculate this way. Psi of t, an operator, psi of t, like this. Now, if I have a mixed state, I have 4 terms. Can you see that? You have 4 terms. Because this psi of t have 2 terms, like that. And this psi also have 2 terms, like that. So therefore, if you multiply out, you have 4 terms. Does that make sense to you? You have 2 terms here. You have another 2 terms here. If you multiply them out, you get 4 terms total. So you have mixed these terms. And these are all in the textbook, explain it, and you can read them. And because assigning a new homework for the next week, we'll use this particular knowledge. And that's the one that I wanted to cover last time already. But this time, I just gave you a quick idea how do we do the calculation. Now it's time for us to move on to the new topic. And this topic becomes a little bit of, it's a continuation as we did last time. And so this will be our section number 4. So section number 4 starts now. In this case, we will work on called Finite Quantum Well. Previously, we called particle in a box, but now here we call it Finite Quantum Well. And here is something, it's slightly more complicated, but not overly complicated. Let me show you what the model looks like. Here is our system. So here's our system. So our system is defined by the boundary conditions, which is, here we have a system that behaves like this. This is horizontal axis, tells you that that's the x coordinate. And then the potential has a well like this. So between negative a over 2, positive a over 2, the potential inside the well equals 0. Beyond these twos, it has a constant value, which is at V0. So in other words, over here is V0, over there is V0. So now the particle can survive in many different places. Not only in the well, but also can survive over there. So these are different places. For this reason, and I'm going to label these different places, this region on the left, I call it region number 1. So we have one region on the left, it's called region number 1. In the well itself, I call it region number 2. And this part, region number 3. And we always stuck with these letters, so that way we know what we are talking about. And that's the structure look like. And this is actually semiconductor quantum well. In the book, I showed you quantum well. And that's called quantum well. People usually write the following way. That's called quantum well. And that's usually you use. So this is the one which we use. Now, I'm going to show you mathematically what this looks like. So here's a boundary condition for potential. So for boundary potential, V is going to equal 3 segments, which is involved. V equals 0, which is 0 here. In this case, if my x is larger than negative a and smaller than or equal to a over 2. So this is the called the inside the well. And this essentially is region number 2. So this is the region number 2. The other region, we have a V0 if x larger than a over 2 or x smaller than a over 2. And this region number 3. And here's region number 1. So we have 1, 2, 3 regions, which are related. So then the wave function, we will also use the phi 1, phi 2, phi 3. The thing that we are going to calculate is exactly the same thing as we did in the polynomial box. So these are the 3 regions. We have 3 wave functions connected to each other. Now the boundary condition for the wave function. Remember, the boundary condition for the potential we have already listed over there, but this time we will have a boundary condition for the wave functions. And this part becomes a little bit convoluted because we want to make sure you guys understand what we're talking about. So this is the wave function. Now the wave function, the boundary means that phi 1 in the left and phi 2 on the right, these two must match. Must match. What do you mean by must match? Well, when a over 2, x equals a negative a over 2, and these two wave functions must be the same. So these two wave functions must be exactly the same. That means the boundary condition. So whatever the value you take, and I have to, put a name sign here. And has to be exactly the same. Similarly, between this particular boundary, so for the I2, a over 2, positive a over 2 has to equals phi 3, a over 2. So these two must be exactly the same. So this one and that one must be exactly the same. So the boundary in this case. Are we good so far? In other words, that's where the boundary condition goes, which means if I have the same boundary condition, and so we have 2 boundary conditions, and that's the 1, 2, we have 3 and 4. 3 and 4 is a derivative of these ones. In other words, just save my time, I simply put a prime equals prime, prime equals prime. Okay, I just saved my time. In other words, this is just first order derivative. First order derivative, that means first order derivative. First order derivative with respect to x. So first order derivative with respect to x, they all exactly the same. So both the values themselves and derivative themselves also are exactly the same. So this is the one we have. Okay. In other words, you're going to see us, we're going to use 1, 2, 3, 4 all the times whenever we got the wave function. Now then, our next job, we will work on systematically find the wave functions for different regions, one at a time. And I'm proposing we're going to work on 2 regions first. Regions 1 and 3 first. We work on these 2 regions. These 2 regions have the symmetry in the sense that, did you see here we have a potential of V0, and this side also potential 0. So we can use directly these 2 regions first. So you're going to see me, I'm going to write down these wave functions. Let's look at these 2 regions first. So the Hamiltonian is now equal to this part, h squared. Now, instead of use the partial, we're going to use derivative because it's just one dimensional, 2m dx squared. That's Hamiltonian. This first term is the kinetic energy operator. That's what we have. So we have d squared over dx squared and h bar squared over 2m and put an negative sign in front. And the second term is we have a potential V0. And this is a Hamiltonian which we have. Once we have a Hamiltonian, we have a time-independent Schrödinger equation, which means we're looking for phi equals E phi like this. Now, in principle, I have to use I, but just highlight in such a way that they all definitely have I. In other words, here my phi is really phi sub 1 or phi sub 3. Just save my time to write them, because otherwise everywhere I have to 1, 1, 1, 3, 3, 3. It just takes time and to write them. So all I did is just basically have this expression. So now I'm going to plug this one into this equation. Plug this one into this equation. So you will see me write down h d phi 2m dx squared. So that's the first term. And the second term multiplied by v0. And my right hand is just d phi, like this. And this differential equation is also quite standard. Let me move all these terms to the right-hand side, so therefore my first term will become positive to make things a little bit simpler. So I move to these terms to the right-hand side. And I also will use the simpler notation. Double primes to representing the derivative. And this move to the left-hand side become negative. So I will have e minus v0 phi, like this, equals 0. And that's the equation which we have. And I want to, again, get rid of the coefficient on this. So I just divide by h bar squared times 2n. So then my equation looks nicer. 2n e minus v0 divided by h bar squared phi equals 0. Are we good from here to there? Are we good? Good. So I didn't do anything, just all these terms times 2n. 2n term is gone, and h bar squared divided by like that. Okay. You good? Any questions? Now, once we got this point, folks, we almost can stop here completely. The reason was this equation, just phi, we're going to denote this term here, this entire term, called k squared, which is called k squared. It just takes time to write them. But k squared and phi equals 0. And this equation is exactly what I wrote in the beginning. And this is the standard equation: x, y, b, y prime, c, y equals 0. And this is the same differential equation. You see, come back again. There's no big deal. So then you can immediately see my lambda squared, it just equals k squared minus k squared, like this. I just want to make sure. Oh, forgive me. I made a small mistake here. Folks, I'm going to call negative k. Folks, I'm going to call this term negative k. So they mean the same thing, but negative k. So then my k, my lambda equals positive k, like this. So that's the term which we have. And I'm going to stop here immediately, because I want to leave some time for the quiz for you guys today. And I will explain why I changed my mind in the beginning, get k squared versus negative k. And I'll explain why the reasoning underlying this. Okay, so, and this part is extremely important because that's the key side of this. Okay, so we stop over here, and we give you enough time for you guys to take the quiz today. All right, stop recording.